This is the Google form quiz that we looked at as part of some work during class yesterday. Looking at the results, did very well as far as answering the questions, and it's very crucial to understand the basics of the mass spectrum graph. So going in order of the questions, question number one, majority correct. Which one is the most abundant isotope of this element? At this moment, we don't care what element it is. We just look for the intensity, which one happens the most often. If we had this sample and put it into our machine and we separated the isotopes due to their masses, we get out of our sample, there's a whole bunch of these that are isotope 48. So the most abundant, because we're looking for the tallest peak, which would result in the most percent in abundance in nature, and isotope 48 is the correct answer for question one. Question number two, the question was which isotope is the least abundant. I did mark the answer key correctly because it's so close to which one's which. It's very hard to tell on the computer which one's the least abundant, and acceptable answers would be 49 and 50. If it was marked incorrect, I only had one of the answer choices. Looking at it, man, it's a toss-up. Very hard to tell, but definitely they are the least amount, and because their peaks are very short, but they're pretty equal in their percent abundance, so it's really difficult to say which one's the least abundant. All right, question number three. So what element is represented in the mass spec below? Well, I got to look at my range. I have 1, 2, 3, 4, 5 isotopes. I have 5 isotopes that are representing this element. And I know that the lightest is isotope 46. And I know that the heaviest is isotope 50. And so I can look on the periodic table and I can see that there's only a few elements that will fit that range of 46 to 50. And so if I look on the periodic table, 46 to 50, well, there's only one element that meets that criteria. Scandium is too light with being 44.9. I don't have any isotopes that support that element being represented here on the mass spec graph. Cannot be vanadium because the mass is too heavy. I don't have any isotopes greater than 50, but vanadium's average atomic mass is 50.9. So the only choice is titanium here, okay? But I'm looking for what is the average mass. Now I can calculate it without doing some calculations. I know in my head that my mass has to be between 46 and 50, but because I have so much in abundance for isotope 48, that I know that my average mass is going to be very close to 48. And so I asked you to calculate the average atomic mass from this data. Sorry about that. And it can be done mathematically, and I need you to be able to do that because of the lab I'm going to ask you to do tomorrow or today. Anyway, let's do that math calculations real quick. So I'm going to clear the board here. And so I have these numbers, and I'm asking you to get information and calculate mathematically from this mass spectrum graph. And here's what I know. I know that isotope 48 is the most abundant. If I look at the relative abundance, we can use it not as don't think of it as a percent. You can think of it as a number of how many atoms, okay? So this line right here is worth 100. These lines down here are worth, 46 looks to be, 15. 47, a little bit shorter, so I'm going to say 13. If you say something different, it's okay, but it just needs to be less. Isotope 47 is less in abundance than isotope 46, and so that's why I chose a smaller number. Now isotope 49 and isotope 50 shall be less than isotope 47, but they look to be about the same. And so that's about, let's just say 10. All right, I'm gonna get rid of that right there because I don't want that just yet. All right, so I need to find percentages here. And percentage is done through finding part over whole. So part over whole equals x over 100. I do that in the form of a proportion. And so I have parts and I have a whole. So if we put these samples in here, and this is the number of atoms, if I say the y-axis is just number of atoms, we can use and make up numbers that will make our average mass mathematically very similar to the one on the periodic table, but it's all about the data that's proven on. So there's a wider range of answers for this problem. So anyway, let's do the math. And so I need to find out my wholes, or my whole. Well, let's add all these numbers up here. We have 100, we have 15, we have 13, and we have 10 and 10. All right, so that's going to be my whole. So we have 100 plus 10 plus 10. I believe that's 120. 120 plus 15 is 135. And then 135 plus the 13, I got 148. That's how many atoms were in our mass spectrum machine. Out of those 148, let's calculate the greatest, most abundant isotope. And we should get an answer close to, well, 100, because it is the greatest peak. And so if I say 100 over 148 equals x over 100, I cross multiply, divide, and this is going to give me my beautiful percentage. So 100 times 100 divided by 148, I get a percentage of 67.5676. All right, and I'm going to go do and calculate the remaining of these isotopes. All right, through the miracle of technology, we fast forward and all the information for the other remaining isotopes and the percentages have been calculated. And so we know that the other four isotopes, their percent of abundance is going to be quite a bit less than isotope 48. And so if we look at, highlight those in red, I calculated the average mass for isotope 46, 47, 49, and 50. Remember, 49 and 50, I said that they are the exact same. And so I'm going to use that same percentages. I actually did the math and said, if I have 5 isotopes, I know that of our sample of 148 atoms, each one accounts for a different amount of abundance for that isotope, but they all total together to equal 100%. Now I use the full mill numbers here, so I don't shave any numbers through my calculations, because when I change numbers as I do each calculations, I become off. But these numbers added together, the percents of each isotope, equal 100 spot on. So again, I can find out the information from the graph and get numbers from the graph, and that's what we're asking you to do. When it's not provided, it actually is part over whole. 48 has more parts to the whole than the other 4 isotopes. All right, so now we're going to calculate the average atomic mass. All right, again, through the miracle of technology, there's the answer. Bam! Now I got to take the mass, and since I'm using a mass spectrum graph, I'm using the isotopes of on the x-axis that's provided for me. The biggest thing that I saw in some of the calculations that you showed me on your work on questions 3 and 4 was us not handling the decimal properly. Remember, you don't have to move the decimal 2 places to the left if you do not choose to. You can do it like the Pogel note stated, that you can put your percentages in the form of a percent, but at the very end, after you multiply mass times percent, then you divide it all by 100, and that'll move your decimal place at the end. Or you just know that, hey, you need to move your decimal. I mean, it's just, you can handle it different ways, guys. But when we don't handle those properly, it gets a little awkward, and we mess up, especially when you have lots of isotopes to handle. We got 5 isotopes here. I've done this a couple of different ways, and the answers end up being very identical. We have an average mass calculated from this mass spec graph, and using the graph to actually get numbers, mathematically they end up being the same. I'm going to provide some information that proves that in just a second. But again, we get an average that's very close to 48, but because of isotope 46 and 47 being lighter, and if we look at their parts, they are about twice as abundant as isotope 49 and 50, which is heavier, which makes the average dip below 48 on the periodic table. Or dip below 48. It doesn't match up exactly because we're making up numbers. We're kind of gauging and ballparking this information. We don't have exact numbers. That's why it's going to be so different from the periodic table. So different meaning that we may be off quite a bit, because on the periodic table I see titanium is 47.87 or 47.867, but I am really close. And again, I did this twice. Let me get that answer for you. All right, so I did this one using numbers that are different. I made up numbers with lengths of lines. And so this circled numbers here, I said are lengths. This one is the most abundant isotope is 10 whatever unit long. This one's 2 long, 1.8, 1.7. I still got my total, okay, which is my whole. And these are the parts, and so my percentages are calculated here, but I left them in the form of a decimal. Now I got different information from the graph, but mathematically they end up being extremely close to the percentages that I just did using the number of atoms. And so I end up bottom line with this answer. It's a little bit different, but overall it's very similar. I expect that you should be able to do that also when you have a mass spec graph and you're asked to get information mathematically calculated about calculating its average atomic mass.